Okay, today I'll be talking about post-quantum zero knowledge and signatures from symmetric key primitives. And this is joint work with Sebastian and other colleagues at Graz and also Microsoft Research, Princeton, and uh, Claudia Orlando in Denmark. So first, as a just as a general background, so what we're trying to do today is applications to zero knowledge and digital signatures. But to focus in on digital signatures, so as a very quick review, a digital signature, you have a signer and a verifier. The signer has some message that they want to sign, and they have some secret key. So they go ahead, sign that message with their key, and the verifier can go ahead and using the public key of the signer. Verify that the message was actually correct. So that's a signature, and we've known how to do signatures for probably like 40 years now. And okay, so what are we doing here today? So today we're talking about post-quantum signatures. So the idea is with the advent of large quantum computers, the basic assumptions that we rely on for our signature schemes are broken. And that includes the RSA assumption, discrete log assumption, anything based on factoring. So even though we don't believe that quantum computers that can break these exist today, and all of our communications and we go online is still secured by these quantum insecure schemes, uh, it's kind of we're at the turning point where we believe in the next few decades it's feasible that there will exist these quantum computers. So there's a large effort now in a NIST standardization process, which we'll talk about later, to build quantum primitives. So one of the primitives that we don't really have a great candidate for is digital signatures, and there are various paths to get post-quantum digital signatures based on some of them based on new hardness assumptions like lattices, message codes, and isogenies. You have also a class of schemes based on symmetric primitives only, because symmetric primitives aren't affected by the quantum attacks. They're just subject to Grover's algorithm, and if you basically make the key longer, you're okay. So there's what's known as hash-based signatures, Sphinx being the well-known one. And the question is, can we build? Are there any other paths to building a digital signature scheme from just symmetric primitives? As a high-level view, the answer is yes. And what we do today is we make use of two recent advances in two areas of cryptography. One is there are new symmetric primitives that are highly optimized to have very few multiplications. And there's also new practical zero-knowledge proof systems that allow you to prove things over general arithmetic circuits. So combining these two things, these two new advances, as we'll see today, you can build a new quantum secure signature scheme that's just based on symmetric primitives. So as a review, again, we rely on what's known as a Sigma protocol. A Sigma protocol is a three-move protocol, and basically you have a prover who sends some commitment, the verifier sends back a challenge, and then the prover goes ahead and sends a response to that challenge. This is the way we just showed it here. It's an interactive proof, but it's a well-known result from the 80s. The Fiat-Shamir heuristic shows how to take this and make it non-interactive. So, can we build digital signatures from Sigma protocols? Yes. The way you do this is you generate here SK is just a random key. That's going to be the key for our signature scheme. X here is the key for the one-way function. You take your secret, you generate a random secret key, apply the one-way function to it. Now you have your public key for the signature scheme. And the idea is that you prove knowledge of the secret key. And that's how you take a Sigma protocol and create or an identity scheme, where you take a non-interactive Sigma protocol and you have the signature scheme, and you prove knowledge of your secret key. Um, and the message here is bound because it goes into the hash that creates in the non-interactive version. The message goes into the hash that creates the challenge. So you bind the message to the signature. You're proving knowledge of your secret key bound to a specific message, and that's how we get a signature. So Sigma protocols for arithmetic circuit. ZKBOO is a paper from last year, and they generalized and simplified the idea of MPC in the head of Ishai et al. And the way that this works basically is you take a circuit, and you can take a general arithmetic circuit. They do it for Boolean circuits, and the way you do it is you take your circuit and you divide it into three shares, and such that you can run the computation on each of the three shares separately, and you get three views. But each of the three shares, each share reveals nothing about the circuit that's being composed, that the values in the circuit. And in fact, two shares reveal nothing as well. So you can reveal two shares and reveal no information. But the idea is that you repeat this many times. You have a challenge response protocol where you have to open up your challenge to open up two shares. So you run the circuit, you commit to your 3 shares, your challenge says, hey, open up these 2 shares, and by that you can check the consistency of the 2 shares, and repeating this multiple times, you can get negligible soundness. The efficiency of this scheme, so unlike snarks and other succinct proving schemes, zero knowledge proof schemes, this is not succinct, and the transcript size as well as the runtime depends heavily on the circuit, and in particular, adds are free, but it depends heavily on the number of multiplications in the circuit. Okay, so first thing we did is, and I'm not going to give the details today, although this was one of our large contributions, is we improved the version of ZKBOO. Remember that it's a linear protocol, so anything helps, and we reduced it by half. So these were a series of optimizations, each one pretty small on its own, but we found lots of places where we can improve ZKBOO. And the nice thing was our improvements didn't add any extra computational cost. They basically made use of some inefficiencies in the original protocol and improved it to now reduce the proof size less than half. So again, when you're talking about a linear scheme and trying to optimize signature sizes, that's a pretty significant computational cost. And also, these changes aren't actually limited to signature schemes, but if you wanted to use a proof scheme, ZKB++, as we call our scheme, is a drop-in replacement for ZKBOO that just gives more efficient proofs. Okay, so signature schemes from one-way functions. The problem is that Fiat-Shamir transform, as we described before, isn't secure in the quantum random oracle model. And the idea is Fiat-Shamir gets its security using the idea of rewinding, but quantum computers can't. You can't rewind quantum state, and it's not clear how to translate the security of Fiat-Shamir into a quantum world. So to get around this, UNRWA devised his own transform, analog to the Fiat-Shamir transform that gets around the problems of Fiat-Shamir. So let's take a quick look at the Fiat-Shamir transform. And the idea is, again, and this is Fiat-Shamir specifically with ZKBOO. So you divide the circuit into your 3 parts. So each of these 3 sets of green lines represents a division of the circuit. You decompose the circuit and you run them. You have these 3 green things are the 3 views. And you commit to each view, and then you do this multiple times in parallel, again, to get soundness. Then you take that all up, you hash it together, and you get a challenge. And based on the challenge tells you which, for each iteration, for each parallel iteration of the protocol, which 2 of the 3 views that you reveal. And so for each iteration, you review 2 views. Again, that means that you're not revealing anything about the actual key that you're proving, but you're proving consistency by revealing 2 views based on the challenge, and you get soundness that way. Okay, and the message, as we said before, is included in the challenge, and that's how you get negligible soundness. So the problem here, as we said, is the security here is based on rewinding. And the high-level idea is if you rewind the protocol and give a different challenge, you would get different views to open. So if you consider, if you have the ability to rewind, you can run the protocol once, get 2 views, rewind, run it again with a different challenge, get that other view, and now you can extract. But if you can't rewind, like in the quantum world, this doesn't work, and there's no proof. There's no security proof, at least for this transform. So UNRWA's transform comes with a little neat trick, and it says, okay, in addition to what you do in Fiat-Shamir, you also send a permutation of each of the views. So here, these are of each of the possible responses. So again, you commit to your views, and there are 3 possible responses. Either you have to open 2 of the views, and there are obviously three different ways you can open 2 views. So UNRWA says, in addition to what you send in Fiat-Shamir, go ahead and send a permutation of each of the 2 views. And in particular, the assumption is that the simulator has this permutation key, and therefore it can undo the permutation and extract the witness by looking at all 3 views, undoing the permutation, and saying, hey, okay, now I have all 3 of the shares, and I can extract. And you do this in particular without the rewinding because you're given a permutation. In practice, this is actually easy to implement. You don't need to really use a permutation, but it's shown that anything, if you have a random oracle output with a size that's equivalent to a permutation, it's indistinguishable from a permutation. So you don't really need to construct this permutation, but you have to just give something an output that's kind of that's the same length as that. So if you look at then, UNRWA's transform has a significant overhead, and the overhead is you have these, instead of now sending just one on the left, you see in Fiat-Shamir, all you send is 2 views. In Unrun now, you send the 2 views you were going to send originally, but you also send 3 times that. Because for each view, you also send the permutation, which is the same size as the response. So you, instead of sending 1 response, you send in something that's the size of an additional 3 responses. So it's a bit inefficient. So one thing we showed is how we can optimize Unruh for our protocol. Because notice that each of these are different responses, but response 1, 2, and 3 actually overlap. Each of them opens up 2 views, but altogether, there only are 3 views total. So we showed that you can regain security. You don't actually need to give a permutation of each response. You can give a permutation of each view. And moreover, we showed that another one of our ZKBOO optimizations, for the view that you're opening, you don't actually have to even include that permutation, because the verifier can construct the permutation itself and recompute the hash. So all that you actually have to give is the 2 views that you're giving in Fiat Shamir plus 1 additional view. So we went from having an overhead of another 3 times what you had to send to now send only about 50% of what you had to send in the basic protocol. So that's G1, G2, G3 are now the 3 views, and you only have to send things in the order of the views and not the order of the responses. So I'd like to now turn over the microphone to Sebastian, who's going to explain how we use these ideas to actually construct signature schemes in practice and tell us about the performance of those schemes.
Thank you. So now we turn to the concrete instantiation. So our first instantiation is called Fish, which is based on the future mirror transform, where we take the ZKB++ and the one-way function and turn it into a signature scheme. And then we have a provable secure digital signature scheme in a random oracle model. And we do also do the same for the Unruh case, where we take the same ZKB++, the same one-way function, but now use the Unruh transform to get Picnic, which is then signature scheme provable secure in the crew realm. Right, so we still have to select the one-way function, and that's what we are going to look at next. So let's start with the signature size. As Stephen already mentioned, the efficiency of the Sigma protocol heavily relies on the number of multiplications in the circuit. So so we have to consider the number of multiplications, but also the ring or the field that we use to represent the circuit. And then the signature size is composed of one constant factor, which is some kind of depends on the security parameter, where we have where we include the commitments and PNG seeds. And then there's one factor that depends on the number of multiplication and the size of the ring. And as a first step, we want to minimize this size that depends on the circuit itself. So we surveyed different possibilities to build the one-way function, where we've looked at standard primitives like AES or SHA-2 and SHA-3, but unfortunately they have a really high number of multiplications and rather unsuitable to build the one-way function. Then there is a new trend to build lightweight primitives, where you optimize some parameter, and in many cases you can come up with primitives that optimize the number of multiplications. And we've identified that a low MC for us in this case works best, because it kind of gets the smallest number of multiplications. And if you compare that really in terms of what's the difference in signature sizes, if you, for example, took AES with 120-bit security, you'd get signatures which are roughly like 162 kilobytes large. And if you take this at the same security level, low MC, build a one-way function from low MC, you arrive at 33 kilobytes. So there's a large gap here, and so we decided to investigate low MC further. So what's low MC? It's a lightweight block cipher design, where one has options to optimize for different metrics. So it allows to select parameters to minimize the number of ends, which is interesting for us, but also to minimize the number, the end depth and the number of ends per bit. Yeah, and so we've chosen instances where we have the same where the block size equals the key size, and also where the data complexity equals 1, which means in our scheme, an adversary only ever sees one ciphertext plain text pair, and so we can reduce the data complexity here, which allows us to go for smaller parameters. And there's still some possibility to vary these parameters, and where we essentially fix the block size, the key size, but can still vary the size of the S box that is used in LowMC. And what we observe here, that if you reduce the number of AND gates, which means that the signatures become smaller, which is on the left side here, you have another component of LowMC, which is a linear part, which gets more expensive because you have to repeat it more often. And so you'll get smaller signatures, but the performance is a little bit worse. On the other hand, if you optimize for speed, then you can use more AND gates, get larger signatures, but they're really fast. We've chosen instances which are kind of somewhere in the middle, and which are a trade-off between signature sizes and runtime. So right, so let's compare that to some other post-quantum schemes. So when we started with Fish and Picnic, we've had so signing and verification took like 30 milliseconds and verification 17 milliseconds. During the process, also preparing our signature schemes to submit to NIST, we were able to optimize that quite a lot, and that down to half the runtime. And signatures in this case are like 129 kilobytes, and in the Fiat-Shamir case, and 200 kilobytes in the Unruh case. So let's compare that to Sphinx, which is also a digital signature scheme, which is only depends on hash functions. And we came close. We're getting closer to their signing times. Their verification is really simple, so we can't beat that. And here we see that they have kind of a trade-off where they have larger keys but smaller signatures, and we have really small keys but larger signatures. And then if you're happy to make assumptions on and take into account like lattice-based schemes or other assumptions, you get a whole lot of different schemes which perform in various categories better than ours, but have larger keys or they have larger signatures. So there is not a perfect schemes, but we have a wide variety where you can choose from depending on your use case. Right. So yeah. So as Stephen already mentioned, NIST is looking for new for post-quantum candidates, for example, for signature schemes, but also for public key encryption schemes and key exchange protocols. And they're also asking for different security levels, where they start with what they call L1, which is kind of, one could think of, it's like 64-bit post-quantum security. And then there's, on the other hand, the larger instance with L5, which is on the other hand with on the other side with 128-bit post-quantum security. And if you take that into account in our instance selection for L1, you'll get really, really small signatures, and they're also quite fast, where we end up with signatures of the size of 33 kilobyte, which is a lot smaller than in the L5 case. Right. So to conclude, we've presented ZKBOO++, where we were able to improve the proof size to half the original size, which but which is compatible with and can be used as drop-in replacement for the original ZKBOO. In the application of Unruh transformations to ZKB++ and our signature scheme, we were able to reduce the overhead from a factor of 3 to a factor of 1.6, which is quite a lot, and which translates to quite a lot of saving in the signature sizes. We've presented two new efficient signature schemes, where one is provably secure in the random oracle model, and the other one is provable secure in the quantum random oracle model. But the improvements on ZKB++ and unruns transformation doesn't also has applications beyond the digital signatures case, and they also apply to any non-interactive zero-knowledge proof for arithmetic circuits in a post-quantum setting. Right. As I said, we've submitted this to also to the NIST competition under the name of Picnic, where we have now Picnic FS to refer to the Fiat-Shamir based signature scheme, and Picnic UR, which refers to the Unruh transformed signature scheme. But this is also a very young field, so on the one hand, one can look for alternative symmetric primitives, which maybe even have less multiplications than low MC. And there's also a lot of work to be done in the special case where an adversary only sees a very limited number of plaintext ciphertext pairs, which is a rather unusual setting for a block cipher. So more analysis there would mean that we can choose more aggressive low MC parameters, which would also reduce the signature size and also the runtime. But also any improvements in the Sigma protocol and the proof system will lead to improvements in the signature scheme. Yeah, then there's also, of course, the topic of side channel resistance. So that's also what one can look at in here. Right. So thank you for your attention. We've published a website now, which includes all the code and also the specification for the for NIST's post-quantum competition. And if you're interested, these are the links where you can look at the specification and the code and the paper. Thank you. Yeah, so I mean, there's it's a little bit trickier here to analyze such. And so in the computation, you never really use the original secret key, but as a linearly shared secret key. And in each round of the protocol, you will have new shares. So the challenge here is that you have to extract one share that is not revealed in the signature. You'll have to extract from one trace, because then it's not reused. So this is maybe a little bit different from other schemes where the same key is reused in many in every computation, and you'll have many traces where you can extract the secret key from. And so I think this is also a rather maybe a more special setting to do side channel analysis.
You mentioned in your submission to NIST that you submitted Picnic, but it didn't seem like you submitted Fish.
Yeah, we've renamed to be more consistent. So it's now called Picnic FS and Picnic UR to refer to the same idea of a signature scheme with the different transformations.
Right, but I noticed you mentioned that the Picnic was resistant to the quantum random oracle model. Is there a problem with the Fish scheme, the Picnic FS?
Yeah, there's no problem per se. It's just that to get the provably secure, it's currently unclear how you would translate the Fiat-Shamir transform to the QROM. There is some recent work which has some analysis on that, but requires very strong properties of the Sigma protocol. Then you can also translate that, but we don't achieve these properties.
Hi, great talk. So, is your non-interactive zero-knowledge proof is applicable for other signature primitives like ring signature or group signatures?
Yeah, probably. If you can build a statement that you can where you so if you can build a statement and you build the signature based on that statement, ring signature, group signature on that statement, that should be possible.
Thanks.